Okay, class, we're going to continue this discussion on chemical reactions and stoichiometric problems. And now we're going to take up the issue of determining the limiting reactant in problems in which we are given so much of reactant A and so much of reactant B, and we have to determine which one is limiting, which one will determine how much product we can form. Just as in our example of assembling a radial flyer wagon where we determined that the number of axles, I believe it was actually limiting. So let's do a chemistry problem. Let's consider the reaction of magnesium with nitrogen gas to form magnesium nitride. And I show you the balanced reaction. Always, again, make sure the reaction is balanced. And I say that we start with 35 grams of magnesium and 15 grams of nitrogen gas. And the question then is how many grams of magnesium nitride can be formed? Well, how do we determine this? Well, again, we have to base this analysis not on the mass of the reactants, because the mass will fool us, just as the number of pounds of wheels and wagons and tongues and axles might fool us. We have to convert the mass to the number of moles. We usually do this right away by taking the mass of magnesium, for example, and dividing by the molecular weight, or the molar mass, of 25 grams per mole to convert that to 1.44 moles of magnesium. Likewise, we take the 15 grams of nitrogen and divide by the molar mass, which is 28 grams per mole, to get the number of moles of nitrogen gas, 0.535 moles. Now that we have the number of moles of the two reactants, we have to determine which of these is limiting. Which of these will determine the amount of product that can be formed. Now, the way I usually do this, and I recommend strongly that you always lay out these problems in this pseudo-graphical manner, is I start with the first thing I see, which was 1.44 moles of magnesium. And I ask myself, if I have that many moles of magnesium, how many moles of nitrogen would I need to completely react with that many moles of magnesium? Now, here you have to look back at the balanced reaction to see that there's a ratio of 3 magnesiums per 1 nitrogen. So you would actually need 1/3 as many moles of nitrogen as the number of moles of magnesium that you started with, a 1:3 ratio. So if you have 1.44 moles of magnesium, you would have needed, and notice the little arrow, you would have needed 0.48 moles of nitrogen. Now, did you have 0.48 moles of nitrogen? Well, yes, as a matter of fact, you had more than that. You had 0.535 moles. You had nitrogen to spare. When you do that analysis, it immediately tells you which of the reactants is limiting. The magnesium is limiting. And my advice is that once you have determined which of the reactants is limiting, draw a box around it so you don't forget. I mean, it's easy to forget these things, so draw a box around it. Now, just in case you had written a reaction starting with nitrogen plus 3 magnesiums, or you had looked at the nitrogen first, if you have 0.535 moles of nitrogen, how many moles of magnesium would you have needed? You would have needed 3 times as many. 3 times as many moles of magnesium due to the 3-to-1 stoichiometric ratio for this balanced chemical reaction. Or in other words, notice the arrow, you would have needed 1.605 moles of magnesium. Do you have 1.605 moles of magnesium? No, you had less. You had 1.44. So again, this reinforces, this states again, that the limiting reactant is magnesium. Now, once we have identified the limiting reactant, this then enables us to determine how many moles of the product we can form. Magnesium is limiting 1.44 moles. Look at the balanced reaction and the stoichiometric ratios. You can form 1 mole of magnesium nitride for every 3 moles of magnesium. So here you have to multiply the 1.44 by the ratio of 1:3, 1 product per every 3 reactants, 1:3, to get the number of moles of the product that you could form, which is 0.48 moles. Okay? Now, if you're asked for the amount, how much magnesium nitride, you then multiply by the molar mass, which is the convenient number 100 grams per mole in this case, to get the mass, which would be 48 grams. You'd form 48 grams of product. Now the key is you start with the balanced reaction, 3 to 1 to 1. 3 of the first reactant plus 1 of the second reactant forming 1 of the product. Then you reduce the mass that you start with to moles, and you do this mole to mole comparison, relating that back to the stoichiometric ratio for the reactants. That then enables you to determine which reactant is limiting, which is in excess, and the limiting reactant determines the number of moles of product that would be formed. Okay, now before leaving this slide and this example, this is a very fundamental example. Make sure that you understand limiting reactants and how to determine limiting reactants. But look at the bottom. I asked the question, okay, theoretically, if you started with this many grams of magnesium, this many grams of nitrogen, theoretically you would form 48 grams of the product, magnesium nitride. But what if you actually perform the reaction and you obtain 42 grams of product? This is reality. Sometimes some spills, we can't get it all out of the beaker. We don't let the reaction occur long enough. Maybe there's some impurities or whatever. But if we only get 42 grams and we should have gotten 48, we can calculate the percent yield. This is like a winning percentage. Our team plays 12 games a year and we win 9. Okay, so we have a winning percentage. Same thing, a percent yield. So we should have formed 48 grams, we actually formed 42. So 42 divided by 48, converting to a percentage, 87.5% yield. Not so bad. We'd probably be able to keep our job. Okay, let's consider another type of stoichiometric problem. In this problem, we're told by our boss, maybe we're our own boss, who knows, maybe we're successful as a chemist, but we're told that we want to prepare a certain amount of product. We want to prepare 250 grams of ethyl acetate. That is, this is a reaction of acetic acid plus ethanol to form ethyl acetate. Don't worry about what these are, they're just reactants and products. But we want to form 250 grams of ethyl acetate. And the question is, okay, how much of the first reactant, acetic acid, do you have to start with in order to form 250 grams of this product, ethyl acetate? So here we're going in reverse. But further in this problem, we add an additional wrinkle. We say that from your experience, you know that this reaction only occurs with an 83.3% yield, only an 83.3% success rate for whatever reason. So let's think about this. If you know that the reaction only works and forms a product 83.3% of the time, and you want to get 250 grams by the end of the day, you have to actually try to make more, in this case 300 grams of the product, because you know that it doesn't always work, that you only win or succeed or have successful reaction 83.3% of the time. Now, how did I get that 300? Well, you take the amount that you need to obtain, 250 grams, and you divide by the success rate, or 0.833, the percent yield, to get the mass that you should shoot for in order to really get 250 grams. That's where the 300 comes from. Just try it. 250 divided by 0.833. So in this problem, we have to try to make 300 grams, and we will actually then make 250, which is what we need. So once we have that additional step, and that's a reality step because this happens a lot, we know that our reactions aren't 100% successful. Once we know that we have to shoot for 300 grams to actually get 250, then the question is, okay, how many moles of the product do we have to shoot for? That is, how many moles of ethyl acetate correspond to 300 grams? Well, the molar mass of ethyl acetate happens to be 88 grams per mole, so that means we had to try to prepare or shoot for 3.41 moles of the product. Now then, how many moles of the reactant did we need to start with? Well, if you look at the top reaction, it's balanced. It's a 1 to 1 to 1. So that means this part is simple. If we were shooting for 3.41 moles of the product, we had to start with 3.41 moles of the reactant. Now, we're not worrying about ethanol. We assume that we have excess of ethanol, okay? And the only reactant that we're focusing on is the acetic acid. So if our analysis says that we should have started with 3.41 moles of acetic acid, what is that mass? How much acetic acid? Well, we just multiply moles times the molar mass, which happens to be 60 grams per mole in this case, to determine that we actually needed to start with 204.5 grams of acetic acid. Okay, you got that? We're driving backwards because we want to obtain so much product. We also added an additional step of realizing that the reaction in this case did not have 100% yield. It only had an 83.3% yield, so we had to actually shoot for making more to actually get to 250. Okay, an interesting problem, a real type of problem. Now let's talk about stoichiometric problems involving aqueous solutions, because an awful lot of these reactions do occur in aqueous solutions. And the only difference is that when we deal with aqueous solutions, we're most often dealing with a certain volume of a certain molarity of a solution. Whereas in the problems that we have talked about so far, we've talked about mass, as if we were weighing things out and putting things in a beaker and shaking them up, and we really didn't pay much attention to whether or not there was a solvent. But in the next couple of problems, we're going to talk about reactions in which the reactants and the products are dissolved in aqueous solution. Okay, a typical one of these is an acid-base reaction. And let's say that you perform a titration. Remember, titrations are a particular type of stoichiometric problem. Let's say that you perform a titration, an acid-base titration, and you determine that it takes 23.3 milliliters of a 0.02 molar solution of nitric acid to reach an end point with 0.01 liters of a calcium hydroxide solution. Okay, you do an acid-base titration to reach an end point. And then the question is, what is the molarity of calcium hydroxide in that solution? Okay. Well, first of all, let's start by balancing the chemical reaction. Nitric acid plus calcium hydroxide goes to calcium nitrate and water. And notice that in order to balance this, you have to put a 2 in front of the nitric acid. 2 nitric acids react with 1 calcium hydroxide to form calcium nitrate and water. Now, it turns out we're not going to be so interested in what the products are in this case, because that's not what we're asked to solve for in this particular problem. Now, the way I will usually represent these, and again, I urge you to always follow this type of pattern, is have the balanced reaction, it's the top row, and then below that, have a row of the information you're given, which will either be the mass of the reactants and products, or it will be molarity and volume, as it is in this case, and then use that information, what I call the information line, to then convert to moles as a row below that. And then you operate with that information on what I sometimes call the mole row, and then you go back up to what information you were asked to solve for, which was either how much, what mass, or what, in this case, what molarity of the second reactant. Okay, so we have our balanced reaction, and then we have the information row. Now notice that when I do these problems, and I again suggest that you follow the same pattern, I convert things to the proper unit on the fly. So 23.3 milliliters, I'm going to convert immediately to 0.0233 liters, because I know that I need to be using the dimension of liters instead of milliliters. Because once I have the volume in liters, I can multiply by molarity to get moles. Notice molarity times volume in liters of the solution is equal to moles. Okay, so let's go ahead and do that. Molarity of nitric acid times the volume of nitric acid gives me the number of moles of nitric acid, which is 0.00046 moles of nitric acid to reach this end point in a titration reaction with calcium hydroxide. Okay, well, how many moles of calcium hydroxide will that many moles of nitric acid react with? Oh, I have to go back up and look at the stoichiometric ratios. 2 nitric acids react with 1 calcium hydroxide. So this number of moles of nitric acid will react with half as many moles of calcium hydroxide. That is, I multiply by the ratio 1 to 2, the stoichiometric ratio. Or in other words, 0.00046 moles of nitric acid will react with 0.00023 moles of calcium hydroxide. Now, if I go back and ask, what was I asked for? I was asked to solve for the molarity of calcium hydroxide. Well, that's a piece of cake now, chocolate cake, because once I know the number of moles and I know the volume, 0.01 liter, I can solve for the molarity of calcium hydroxide. And when I do that, I get the molarity of calcium hydroxide to be 0.0233 molar. Okay, so here's a problem, a stoichiometric problem, an acid-base titration problem involving reactants in aqueous solution, where we use molarity times volume as a way to convert to moles, whereas in the other examples we've given so far, we've used mass and molecular weight to convert to moles. Okay, let's see what's next. Oh, a scary looking one, a redox titration. Oh, look at that reaction. I can feel my blood pressure going up. 5 iron plus 2s plus, that's permanganate, plus hydrogen ion, 8 of them, goes to 5 iron plus 3s plus Mn plus 2 plus 4 waters. Could it get any worse? Probably. All right, so here's a reaction. This is a redox reaction. Okay, you can immediately tell because the iron plus 2 becomes oxidized iron plus 3. If you wanted to confirm further, the manganese in permanganate has an oxidation number of plus 7, and it becomes reduced to an oxidation number of plus 2 in the product. So it definitely is an oxidation reduction reaction. This also is an example of a reaction that occurs in aqueous solution, and it is a titration reaction. This is a redox titration rather than an acid-base titration. So what are we told and what are we asked to solve for? So it says, let's say that you titrate an iron plus 2 containing aqueous solution with potassium permanganate to reach an endpoint. An endpoint just as in an acid-base titration, to reach an endpoint. The endpoint occurs after adding 26.45 milliliters of a 0.0225 molar solution of permanganate. What is the mass of iron plus 2 in the sample? Okay, well, let's chill. Let's not be worried about this because we've done a problem just like that. The first thing we do after making sure that the reaction is balanced, and it is, I'll go ahead and tell you that, is we have a row that is an information row. For the iron plus 2, we don't know the information yet. That's what we're solving for. So let's say that's question mark X. That's where we have to wind up. But we do have information about permanganate. We're told the volume and the molarity. Now again, notice that I've immediately converted that 26.45 milliliters to liters, 0.02645 liters, because I can then multiply the volume in liters times the molarity to get the number of moles of permanganate, MnO4 minus 1, the number of moles of permanganate. And that happens to be 5.95 times 10 to the minus 4th moles. Okay, so the question is, if I have an endpoint titration where I've reached the same number of moles of permanganate as the number of moles of iron plus 2 that it will react with, all right, that's what we mean when we reach that sort of equivalence point. So I reached this with 5.95 times 10 to the minus 4th moles of permanganate. How many moles of iron plus 2 would that have reacted with? Well, if we go back up and look at the balanced reaction, every 1 permanganate will react with 5 iron plus 2s. So we multiply by the ratio of 5 over 1. So if I had 5.95 times 10 to the minus 4th moles of permanganate, it will react with 2.97 times 10 to the minus 3rd moles of iron plus 2. Okay. And if I'm asked, and always make sure that you know what you're asked for, if I'm asked for the mass of iron plus 2 in the sample, I then simply multiply that 2.97 times 10 to the minus 3rd moles by the molar mass of iron, which is 55.85, to get the amount of iron in that sample. And that would happen to be 0.1662 grams of iron plus 2 in that sample. So this is an example of using a redox titration to determine the amount of iron plus 2 in a sample by doing this sort of titration using permanganate. Now, I've mentioned at one point that for titration reactions, for them to work really well and be convenient for us, we have to be able to determine when we've reached this endpoint. And I said that redox titration reactions oftentimes show a color change, and in fact this one would as well. As one further wrinkle in this problem, what if our original iron sample weighed 0.286 grams? The sample contained 0.286 grams, but we've determined that of this sample, 0.1662 grams is actually iron. Okay, now that means that the sample may have contained some other material. So you may then be asked, what is the percentage of the sample that is actually iron? In this case, you determine that by taking the actual amount, the mass of the sample that is iron, 0.1662 grams, and dividing by the total mass of the sample, 0.286 grams, to determine that it was 58% iron. It may have had some other stuff in that sample. So if we can do this problem, in which we essentially were dealing with almost everything we've talked about in this chapter, we can balance chemical reactions, we can use molarity, we can look at stoichiometric relationships and determining limiting reactants, or determine how much, if we have a limiting reactant, how much of another product we can form or how much of another reactant we can react with. If we can do this problem, you're ready to go. Okay, you are a chemist. Okay, so we'll probably have opportunities to see if you're ready to go. Okay, this is the end of the chapter on chemical reactions and stoichiometry. See you later.